after the Königsberg bridge problem was solved, graph theory was forgotten for almost 1 century, and it was rediscovered by a scientist named as the Arthur Cayley, who studied the structures of the non-cyclic saturated hydrocarbons. And we know that the hydrocarbons are the compounds that contains only the carbon and the hydrogen atoms. And the general formula of the hydrocarbon is CnH2n plus 2. So these are the chemical formulas of the hydrocarbons. And the structure of this type of hydrocarbons are examples of trees, which are simply connected graphs with no cycles. It is not hard to show that every tree has at least one vertex with degree 1 or leaf, and this observation immediately implies that every tree on n vertices has n minus 1 edges. So we can see in this figures of the non-cyclic hydrocarbons that they represent the general formula of CnH2n plus 2. And if we consider the first methane structure, in which we can see there is only C is one atom, and if we put the value of H, and because n is 1, then we will put 2 into 1 and plus 2, then it comes out to be CH4. So similarly, for this butane, we can consider the C as 2 atoms, and then we will put the value of 2 into 2 and then plus 2, it will comes out to be 6 hydrogen atoms. And the second is that we have seen here that the structure of these chemicals, they represent the tree, and we have seen and studied that the n vertices of the tree has the n minus 1 edges. For example, we can see that each atom of this chemical formula represent one vertex. For example, this H is one vertex, this is second vertex, this is third, fourth, and C is the fifth vertex. So it means that the number of vertices is 5, and we represent 5 as n, and from this n we can calculate the number of edges, and number of edges is n minus 1, and it will come out to be 4. And we can see in this one that there are 4 vertices. Number 1 is this, 2, 3 and 4. Similarly, in this molecule, the number of vertices is 1, 2, 3, 4, 5, 6, 7, 8, because each atom represents one vertex, and the number of edges will be 8 minus 1, that will come out to be 7. So same is the case with all of the other molecules. So since every tree has a leaf, then we can remove it and its attached edge, resulting in another tree. And we can see in this one there is a tree, and we can remove the one vertex and one edge at one time, and we will get the another tree. For example, this is a tree, and in this tree we have removed this one vertex and one edge, and we will come up with this tree. Similarly, in this tree we have removed this vertex and one edge, and we will come up with this tree. So similarly, we have removed one vertex and one edge until we were left only with one vertex. So this removal of 2 vertices and 2 edges and so on, and we come up with only one vertex. And this shows also that the number of edges in every tree is n minus 1. And after n minus 1, because there is only a vertex is left, so we cannot minus 1 from that vertex. And for example, if we go back to the second last one, so here we can see there are one vertex second vertex, it means that n is equal to 2. So if we want to calculate the edges, then we have to use the formula n minus 1. So n is 2, and if we minus 2 from 1, we will get the answer 1. So we can see here there is only one vertex. So from this removal of the smaller trees, we can prove that the number of edges in every tree is n minus 1.